Hello everyone! In this video we will continue to examine topic 1.2, uncertainties and errors, and in particular we will continue to unpack the propagation of uncertainties. Alright, so in the last two videos we examined the propagation of uncertainties under addition and subtraction and under multiplication and division. There is one other category of functions we need to discuss where you need to be able to formally propagate uncertainties. But before we do so, a quick word about this. One thing to know is that these rules for propagating uncertainties through addition and subtraction, multiplication and division, and what are known as power laws are rules that are an approximation of the best thing to do. The best thing to do is to propagate them according to laws or rules that are governed by a set of differential equations. And what that means is that you need calculus, and in fact, a pretty substantial bit of calculus, before you can propagate uncertainties perfectly correctly. So this set of rules I'm giving you are, unlike a lot of what we're going to learn, pretty IB specific. They are good rules. They're super solid. They give an accurate representation of the uncertainty on the propagated value. But they are not sort of exactly right and the exact correct thing to do given the uncertainties. And I'm not going to go into sort of the formal aspect of it, but you can look this topic up if you like on external sources if you'd like to know sort of more about the formal way to do it. I would recommend not trying to wade into that too deeply until you have at least some calculus. But I just thought I would mention it before moving forward. All right. The final operation under which you need to be able to propagate uncertainties is to propagate them through a power law. Firstly, note that a power law is a law of the form y is equal to a to the n. Notice, this is not an exponential. I'm going to repeat it for everybody in case you didn't hear me and in case you make the mistake on your next lab. This is not an exponential function. An exponential function is a function of the form f of x is equal to e to the x. Notice that the base is a number, in this case e, or any value, and that it is raised to the xth power. Okay, it's raised to the xth power. In the cases that we're going to look at, okay, that is power law cases, those are all of the form x to the nth power. So the important variable in an exponential function is in the exponent. The important variable, that is the one that is changing, the independent variable, is the base in a power law function. In this case, it's represented as a. But let's take a look at an example in practice. S is equal to 1/2 t squared. S is equal to 1/2 at squared. This is an equation we will see later on in much detail. You'll become very familiar with it. But in this equation, this is not an exponential function. In fact, it's a quadratic. And a quadratic is a certain type or a subset of power laws. So in this quadratic, all right, if we have some delta t, so some error on the time and some error on a, we need to know what the error on s is going to be. Now, you can actually get this simply by considering the whole thing, this equation, as s equals 1/2 a times t, and simply utilizing the multiplication formula we've seen before. If s is equal to 1/2 a times t, and we have an uncertainty on t, and we have an uncertainty on a, then the uncertainty on S will be the relative uncertainty on S, okay, is equal to the uncertainty on A. Sorry. Back up. Start again. The relative uncertainty on S can be calculated by taking the relative uncertainty on A and adding it to 2 times the relative uncertainty on T. Why? Because there are 2 of them. There's one T, there's the other T. Okay, notice that what that means is the exponent drops down, and now you're multiplying by the uncertainty on T over T. Okay, so you can see how this rule in general, the one that is given, where you take the exponent, drop it down, and multiply by the relative uncertainty on the base, can be sort of extrapolated from our rule for multiplication. So if we're given these values here, we can go ahead and plug them in, and that gives us a total relative uncertainty of 0.408. So we represent our total S as S plus or minus delta S, 8.5 plus or minus 3.5 meters here. Okay, and I'll let you work out sort of that missing step between the relative uncertainty and the final absolute uncertainty. Notice that, okay, so far so good. That rule, though, we already had sort of in the form of the multiplication rule for propagating uncertainties. But notice that this general rule for any given power law can be used for exponents that are not integers, and that is super useful. So if y is equal to a to the n for any interesting value a and any constant number n, then the relative uncertainty on y is the absolute value of that exponent times the relative uncertainty on a. So for example, we can apply it to this function. This t is the period, and we'll see it a little bit later, but t is equal to 2 pi times the square root of L divided by g. Notice that this can be written using exponential rules as 2 pi times L to the 1/2 times g to the negative 1/2. Notice this thing and this thing are exactly the same. And now we have managed to write this entire function in this form, in this power law form. Notice it's L to the 1/2 times g to the negative 1/2. So how do we deal with that? Well, then the relative uncertainty on t is equal to that first exponent drop down times the relative uncertainty on L plus the second exponent drop down, and you could put a negative here if you want, but that's why those absolute value signs are there, times the relative uncertainty on g. And that would be how you calculate the relative uncertainty on t, given this formula here. So I would very much recommend that you work your way through sort of these example problems in order to sort of practice using these propagation skills. You will need them throughout the course. Notice there are many functions, including exponentials, among other things, like sines and cosines, that we will see this year, where propagating the uncertainties through those functions will be a little bit challenging. And we will sort of face those as they come, and I will explain sort of how to go about doing them. The only ones you will be expected to explicitly calculate for the IB on, for example, a test would be the cases of addition and subtraction, multiplication and division, and then any power law, where a power law is of the form y is equal to a to the n, rather than of the form e to the x. Notice the interesting variable, the independent variable, is in the base in a power law and not in the exponent, as in an exponential function.